I hope everyone's having a great evening. I am Mr. Ish. Thank you for joining me for this very quick video where we are looking at this concept of mole, which many of you are familiar with. But this is an excellent unit of measurement. It's perhaps the most fundamental to chemistry, but the primary feature of this, it reconciles mass with other measures. You know the mole has that wonderful quality. When you're looking at anything with regards to mass, then you can use a mole to convert it into other measures. What are these other measures? You know what they are. They can be volume, they can be molarity, they can be your pressure by means of the ideal gas law, it can be with the molecular weight of an unknown. All of these, it's just not this. You can have molality, you can have other units of measures, freezing point depressions, boiling point elevations, all of that has the mole, and in some way, shape or form the mass comes into play. The mole is always defined as such a unit of measure that pure carbon would have a mass of 12 grams, and then that right there gives you the definition of molar mass. Molar mass is always given in terms of grams per mole. A 1 mole of carbon, pure carbon, would give you 12 grams per mole. That's exactly what you have. The other way you can memorize or remember what a mole is, the mole is such that 12 grams of carbon will always have a certain number of atoms, and that will be the Avogadro's number, 6.022 times 10 to the 23. You can just say atoms. And that right there is a good unit of other measurement too, the Avogadro's number, coming again from the concept of mole. If you can remember that a mole is a unit of quantity such that 12 grams of pure carbon would have 6.022 times 10 to the 23 atoms, then you can use mole for anything else. And let me show you what I'm talking about. If you have 1 mole of copper, what are you indicating by 1 mole of copper? Then you just look at its molecular weight, and that's, what is it, 63.55 grams per mole. That's what you have. And then when you're looking at this, if you're looking at 1 mole of copper, you have 63.55 grams per mole times 1 mole of copper, and look what happens. You have this cancel out with this, you end up seeing 63.55 grams. 1 mole of copper, which has a molar mass of 63.55 grams per mole, notice the units are grams per mole for molecular weight, will be equal to 63.55 grams of copper, but it will also be equal to 6.022 times 10 to the 23 atoms of copper. Just because you're looking at carbon as being a unit of standard for the mole, and you have 6.022 times 10 to the 23 atoms and 12 grams of carbon, it doesn't mean that just because you're looking at 1 mole, you cannot have the same number of atoms. You can, because that concept of mole then extends to anything else. 1 mole of copper is equal to 6.02 times 10 to the 23 atoms, just like you can say 1 mole of bacteria would be equal to 6.022 times 10 to the 23 bacteria. That's what it will be equal to. 1 mole of anything is always equal to this right here is your standard. But 1 mole of anything in terms of an element from your periodic table is always equal to that same element's molar mass, but in terms of its mass, because the mole unit cancels out as I've shown you. Let's look very quickly at just a single computation, then that can be it for this particular video, because the mole concept is not overly difficult to understand. Let's end with this question over here. We have 4.7 times 10 to the 20 atoms of X, an unknown element, sample, or compound, whatever it might be. We have to find the number of moles of X. We also have to find the molecular weight of X if you have 1.0926 times 10 to the minus 2 grams of that X. We will start, of course, with this. You have how many moles? You have 4.7 times 10 to the 20 atoms. We can do that, multiplied by 1 mole of something is always, and let's call that 1 mole of X is always your Avogadro's number, 6.02 times 10 to the 23 atoms. That's what we have. The atoms will cancel out, but what the computation will give you your moles of X. You'll do this divided by that, and you'll have 4.7 exponent 20 divided by your Avogadro's number. You're getting 7.8047 times 10 to the minus 4 moles. You're getting here 7.8047 times 10 to the minus 4 moles of X. That's what we have. You know, moles of anything is always equal to your mass divided by your molecular weight. Therefore, your molecular weight is equal to mass over your moles. And look at the units. You can have grams divided by mole. That grams divided by mole is your unit for molecular weight or molar mass. I already have the grams. I'll divide it by moles and I'll get exactly my answer. I'll save this value here on my calculator, and I have 1.0926 exponent 2 minus grams. I've provided that. You divide that by your computed moles. I'm dividing it and I'm getting 13.999. I'm getting here as this other answer right here, 13.999 grams per mole. Remember, grams per mole is a unit for molecular weight. Which element on the periodic table or in the periodic table has that? You can round it up to 14 grams per mole, and you know you're looking here. And here you're not looking just at your ordinary element, you're looking here at nitrogen. That's exactly what it is, because it's a very fundamentally important element to life. Nitrogen, plants very much depend on it. And that's the X you have over here, the unknown. Remember, again, what we've talked about, unit of measurement. Moles is always mass divided by molecular weight. The units of molecular weight are grams per mole. And everything I've talked about, the Avogadro's number is always 6.02 times 10 to the 23. You can utilize that as a very good factor in these type of calculations. Thank you for watching.